So let's continue with this simulation of our Vasicek model. But in order to do that, we need to look to the analytical solution of the stochastic differential equation. Um, Remember that we have this equation 20 that describes the evolution of the short rate r in time, and this alpha, b, and sigma here, these are constant parameters in the Vasicek model. So the model tends to go back to its long-term mean b whenever r is below b. So there will be a positive dRt will have this positive deterministic part. So interest rates will try to go up to get back to their long-term mean b. Or similarly, if r is above b, then this term will be negative because this alpha is always positive. So this will be negative, and it makes the interest rate again tend to go down until they reach this long-term mean level b. So this is the mechanism that sustains this mean reversion behavior. But of course, we have this noise part, which is proportional to this sigma. So we have this volatility term and Brownian motion term. So you can see the analytical solution of this STEs is given in 21, and we can directly use this analytical solution to do our simulation using Monte Carlo, of course. So these increments of the Brownian motion, basically we can use, of course, the normal random variables, and we can simulate the exact solution. Alternatively, you can discretize the original STE using the Euler scheme. So if you apply just a simple differencing to approximate these derivatives and substitute this dt by the delta t terms and dwt, you can again use the standard normals times the square root of the delta t here. So this is also possible to use in your simulation, but don't forget that this will include an extra discretization error compared to the equation 22. Okay, so if we look at now how we can write a code, so you see that we have these first parameters of the model, so you can just assign some values here, and then suppose I want to simulate my single path, so n is 1, that means I'm simulating a single time series of short rates for 50 years. So that gives me m number of time steps if I am doing this simulation day by day. And you can see our for loops. So this is the main for loops to generate our short rates from the Vasicek model. So since this n is just 1, because I want to generate this data for sufficiently long time, and then I want to estimate the parameters and compare with my original parameters here, whether they give close results to the exact values or not. So that's why this is just 1 in this case, but for general purposes, of course, you can have multiple paths that you can simulate. So once we do this, you can see it is exactly following the exact solution we have written in equation 22. So following the same equation, we are simulating our short rate values r. And then I would like to go back and estimate the original parameters from my simulated data. So how can we do that? You can see once I simulate r, now I want to assign this as my y, and my x is given here. So let me go to the parameter estimation part here. So notice that once you have this equation, actually this is simply an AR1 autoregressive of order 1 model in time series. So actually it's a regression problem where you are actually writing or modeling the tomorrow's or next steps, let's say R, in terms of the current step RT with some constant coefficients, and you have the noise term which is assumed to be IID. So this is a regression problem, And the only thing you need to do is once you estimate this regression in terms of A star and B star, you need to go back to the original parameters of the model, alpha, B, and sigma. Okay, so we can do that by solving these system of equations basically. So we regress y on x and we get the coefficients in our beta. So if we run up to here, so we can see that we have our y, we have our x now, and then we can estimate this beta, which includes this A star and B star. Then you just need to get alpha hat, B hat, and you will get the sigma hat. Okay, so and then you can compare with your original values. You can compare with these. So we can see that alpha hat is 1.24, and this was the original value. B hat is here, which is sufficiently close, and also sigma hat sufficiently close to this 0.02. So you can see that especially for B and sigma, our estimation methodology is more accurate. For alpha, we are not that accurate, but you can also expect, as you have more and more data, this estimation accuracy should improve. So you can try, and also similar estimation part can be applied with the real data. But the reason we are first simulating the data is because we can compare the exact values that we assigned with the estimates that we obtain to make sure our parameter estimation is working properly.